CS 682, and to your surprise, there is not going to be a course on quantum computing. This is going to be a course on quantum algorithms, right? We are computer scientists, and I can tell you what kind of math. So I would say linear algebra is a must. What are eigenvalues, eigenvectors, matrices, vector spaces? I will introduce them very, very briefly, but it is good to know linear algebra. Probability, I will use it. If you are really, really interested and you have time, you can pick it up. But then you should be really motivated. Generally, people are very motivated in the first week. That motivation decreases as the time passes in the semester. So be careful about your motivation. So welcome to again this course on quantum algorithms, and the first question I am going to ask is, what is quantum computing, right? Anytime you want to learn something new, that's the question you should ask. What is that thing, right? And the second thing you should ask is, why? Why quantum computing? And this is the plan for today. But since I am a brilliant teacher and really lazy, that means you will tell me what is quantum computing, to use it in the form of computing, okay? In terms of, did you say? Is that to use laws of quantum mechanics for computing? Anyone else? Yes. Okay. Anyone qubits? Go ahead, answer so that I can write it on the board. Make my job easier. Okay. What about others? Sorry? To simulate? Why do I care? I'm a computer scientist. But you are right. This is, you are telling me a use case, right? Why quantum computing? You are telling me what is quantum computing. So when we come to why, I will take that. That is completely correct. That's the best use case, simulating quantum mechanics. But what is quantum mechanics? Okay, yeah, this is the most popular answer and this is the most hated answer according to me. In classical, you use bits. In quantum, you use qubits, right? And I'm going to say that this is like a manager's answer. It is correct, but it is useless. Okay, so let's not worry about it. Again, this, why not use a parallel computer? There are parallel computers in the market. Why don't we use a parallel computer instead of a quantum computer? So yes, why quantum computing? In the some sense, there is some parallelization, but that's not really the power of quantum computer. So one thing which I really want to ensure through the end of this course, yeah, so two things which you should remember is QC is not a parallel computer. It is not a randomized computer. So obviously when you want to understand something, it is always better to understand what it is not. And after 4 months, someone asks you what is a quantum computer and you say it is like a parallel computer, either shoot you or either shoot me. 50-50% chance. Okay, or you say that quantum computer is basically a randomized computer, I can do things probabilistically. Again, I will cut your head off or my head off. 50-50% probability. Okay, so this is something which I really want to drill, that quantum computer is fundamentally different from the classical model, and that's why we are so excited about it. Okay, it is not like a parallel computer. We had parallel computers even before quantum mechanics was there. Not quantum mechanics was there, but the idea of quantum computers came. We had randomized computers before the idea of quantum computing. And I will give you enough examples to show that these are different. Okay, so then this is actually the closest answer. This is very good. Thank you. We want to use laws of quantum mechanics for computing. But why would we like to use laws of quantum mechanics? Why won't we like to use the laws of electricity? Why won't we like to use the laws of biology? Why won't we like to use the laws of whatever, humanity, whatever? Yeah.
One limitation that we are getting right now is that the scale at which we are computing is getting shorter. At the point where quantum laws or quantum phenomena are taking place, which are resulting in errors while computing. So now we have to switch to quantum laws.
Again, yes, you are right in some sense, but you are not answering my question. Why don't we use? Yes.
I think we can increase the computation speed exponentially by increasing the number of qubits which we can compute.
Again, you are telling me, yeah, quantum mechanics, all the answers, but still we are not going to the deeper detail. My question is, forget about quantum mechanics. Use laws of electricity, use laws of biology. Why don't I think about it?
We do have that nature-inspired algorithm to do that.
Exactly, we already do it. Do you know some place where we use laws of electricity for computing? This computer, right? So then actually, before I answer what is quantum computing, I will answer what is computation. Okay, and then you will understand what I am trying to say here. Okay, so again, yes, we want to use laws of quantum mechanics for computational purpose, or to express it, we want to encode our computation in the laws of quantum mechanics. But this is a loaded statement. What does it mean? So let me explain it in the next 10 minutes. First question is, what is computation? And I will answer it in my favorite way. I will ask you to answer it. What is computation? In computer science building, everyone should raise their hand.
Like if we have a machine and we have a sequence of its states, and each state in the sequence, the next state can be obtained from the previous state with just one transformation, that is
Okay, you are very close. So, but you are saying many extra words which are not needed. It is automated calculation, and when we talk about algorithms, we want to say it is sequence wise and things like that, but computation is doing your task in an automatic way. Okay, so even if I have a system which does 2 plus 2 and tells you 4 is a computer, if I don't have to do it, if I don't have to write 2 plus 2 equal to 4 here. So it doesn't matter things are whether things are complicated or easy. What is important is it is done automatically by your device, right? And why will that device be able to do these things automatically? Because that device runs in a fundamental way in some physical law. For example, you have Kirchhoff's law, Ohm's law. You can use them to make your AND or NOT gates, right? And let me not even go to the electricity. Let me take much more basic examples of computers or how you can build a computer. Okay, so the first computer I will make is what I will call a billiard computer. Okay, so you're ready to build your first computer. Okay, you're really drunk in a bar and then you decide to play billiards. Your friend says you are really bad. You are worse than a robot who will hit the ball half the times into the pocket. Okay, so there is a robot which pockets the ball exactly half the time. Is this robot useful? Is this robot a computer? Sorry? Is this robot a computer? What kind of computation can it do?
If you want to generate a binary string,
No. For division. This is a computer. A robot is a computer which will divide by 2. If I want to divide 26 by 2, what will I do? I will place 26 balls in front of this robot. Make the robot hit the balls and count the number of balls which are pocketed. I don't have to do 26 by 2 equal to 13. I will just count the number of balls in the pocket. So this law which robot follows has allowed me to divide by 2. My calculation has become automatic. And as always in all of these computers, there will be some input. I will have to make an input. I have to make sure that I can place 26 balls on the table. I have to have robot hit them. This is the operation, some kind of gates which I will apply, and finally I should be able to extract the in this case, which will be by counting the number of balls which are. So you see the point? So this robot allows me to divide by 2 because it follows this law. Now I will keep changing this law. I will take a different system, this law will change and I can compute different kind of things. For example, for this computer, these will be the laws of electricity which allows me to apply gates and or not which are universal, so I can compute almost everything. Okay, but while we are having fun, let's take one more example. So I create an imaginary insect named row. Okay, what is the property of this row? Again, this is a biological creature which has, some of them have rings on it. And the ring is determined by let's say a dominant gene. You know what a dominant gene is, right? So what happens if the two parents, if at least one of the parent has a dominant gene, then the offspring will have rings on it. That means if one of the parents have a ring, at least one of the parents have rings, then the offspring will have a ring. Okay, so this is the law. Great. Now what can I compute using this insect? Don't shout out, let me know, people raise their hand who can figure out what can this insect compute. 1, 2, good, very good. Good. Others, think about it for a minute. This special insect which has this property, it has a dominant gene which decides whether you have a ring, it is displaying a ring or not, is determined by this gene, then it follows this. Then it can compute OR function, right? Makes sense, right? Now you see why the insect was named row. Okay, and then you can say another thing. Let's say I have some gene therapy. I will just denote it by a very bad looking injection. What it does is that I have the insect. If I put this, it will reverse the gene. That means if the insect did not have a ring, it will have a ring. Drawing is not my strong suit. You will find it out for sure. Correct? So this is not. And now if I have complete control over these insects, correct? That means I can get any number of insects with rings, any number of insects without ring. I can mate them as I like. I can count the rings. I can see the rings. I have enough number of injections. Then I have got a universal computer right here. Because I can create OR gate, I can create AND gate, NOT gate, I can create AND gate using NOT and OR, right? The answer to this question is yes, not just quantum mechanics. You can use laws of any physical, any biological, anything real. If they follow a law, you can potentially make a computer out of it. Okay? Basically, computation is what? You are encoding your computation in a system which follows certain laws so that its behavior is predictable. And just to make sure that these things are clear to you, okay? What is this circuit computing? There's obviously these two mate, right? So if you can't understand my handwriting, let me know. These are two insects, none of them have rings. If A equal to 1, if B equal to 1, then I put injection to both of them, then they mate, then I once again put an injection. What will this do? What will this circuit do? Right? Yeah, AND is a good guess, but that's not correct. Right? So, okay. So at this stage, I will get A and B, correct? Not A or not B. Okay. This is AND or NAND? AND. Okay. People understand what is OR and what is AND, right? Anyone clear, right? Okay, good. So again, the idea is we are encoding our computation in some kind of physics, chemistry, biology, some kind of a law, right? And now by taking these examples now, I think it is kind of clear what we want to do is encode our computation using laws of quantum computing. So QM is quantum mechanics. Encode our computation using laws of quantum mechanics. Then we can perform this computation by a quantum device following these laws. Okay, this is the most fundamental point which says why we would like to have a quantum computer. I want to make sure that this is okay. If there are any questions, let me know. Otherwise, we will move forward. Yes.
There are many systems in the universe, but why only quantum?
Good. That is why. But we have not gone to why. We are still at what. I'm going to answer your question very soon. Any other question? This point is clear. So now you know what is computation. And once you know what is computation, you encode your calculations in a physical device which follows certain laws. If that physical device is a quantum system, that means when it follows quantum laws, then you are building a quantum computer. Okay, great. What is a quantum computer? We know now. A quantum system, device, whatever you want to call it. What do I mean by a quantum system? Which follows the laws of quantum mechanics, right? So a quantum system device QM, a quantum system doing automated tasks for us. Okay, great. But then there are several billion laws, a lot of insects following very, very different laws. The obvious question, which already has been asked, okay, is there any physics major here? Okay, I'm surprised you didn't ask this question, so I will ask on behalf of you. Everything follows the laws of quantum mechanics. Supposedly, right? Quantum mechanics is supposed to be the theory of everything. Now you might say gravity or something, let's not go into that much detail. But yes, quantum mechanics is the theory of everything. So that everything is a quantum computer. Then what the hell? Why are you here? Why are you wasting your precise time and money on me?
So in classical computers, this term specifically, which is referred to as the coherence, is not maintained, which is actually realized in these quantum computers, or at least being tried to manifest, like we are trying to realize in quantum computers. This coherence is specifically the true and
Again, skirting on the issue, but can you make it accessible to everyone here? There are people, there are undergrads, masters, PhD students here. There are people from different departments. Yes.
So in the classical computer, we have bits 0 and 1. But in quantum computer, we use the superposition law to form a superposition of these two bits. Quantum system uses superposition. But in classical way, we don't.
So, okay. So the answer actually everyone can give, right? When you, how many of people have studied quantum mechanics? Everyone, right? At some point, physics in 12th class or 11th class, right? What was the most important part? When Newton looked at the apple, why did he discover gravity and then classical laws? Why didn't he discover quantum mechanics? Because quantum mechanics efforts are not visible at the usual scale, right? So quantum laws, or laws which are different than classical, superposition for example, only exhibits when the system is very small and probably cold, right? So if we want to put our complicated calculations, encode our complicated calculations in difficult quantum laws, the system should be able to exhibit those quantum laws, right? That means the we can only make interesting computations if we are going to control these small systems which exhibit these weird properties. So when I will keep saying weird properties, I mean the quantum laws which we are excited about, like superposition, like entanglement. So quantum mechanics is weird, right? I'm sure everyone who studies quantum mechanics finds it weird. If you're not, then you are weird. No, but it's definitely weird. The laws seem counterintuitive, and the hope is that we can encode many more things as compared to what we can do in the classical laws. But now if you want to use these weird laws, then your system should be exhibiting those quantum laws, right? And that we know only happens when the system is small and cold. And that's the reason why it is so hard to build a quantum computer. You want systems which exhibit these weird properties, but that means you have to control very, very small systems. Okay, so great. So everything is a quantum computer technically, but it's not a useful quantum computer. Whenever I say quantum computer, I mean useful quantum computer which can do more calculations than a classical computer, right? And this is saying why, in some sense, it is saying why because the hope is it can do more than classical computer, right? So answer for why is hope that QC does better than classical computer. And this better I'm going to come to very soon, but what is the reason that we believe QC can do better than classical computer? First, obviously, it is the theory of everything. Before my physicist friends kill me, theory of almost everything, right? So it kind of governs the behavior of almost everything, seems like the most powerful system. And second thing, and which probably is the more exciting thing, it has these weird properties like superposition. Okay, so this was the hope in 1980s, and after around 40-45 years of work, I think we have enough evidence that this hope was actually correct. There are many natural cases where we can use the weird properties of superposition and entanglement and do things better. Okay, so where are we? What is a quantum computer? Use quantum mechanical laws to encode our computation. Why quantum computer? Because the hope is that it does better than classical computer. This better we are going to define now. Again, anyone would like to take a guess? What does better mean? Can it solve halting problem?
So maybe whenever we talk about the performance of an algorithm, we talk in terms of time complexity.
Okay, good. So since you are running ahead, I will stop you. I will ask the first question. What can a classical computer do? At least people from computer science should be able to answer this. There is an abstract model which captures exactly what a classical computer can do. That model is called Turing machine, right? So Turing machine is an abstraction, and we can say that whatever your classical computer can do, Turing machine can do. Whatever Turing machine can do, your classical computer can do. Infinite memory or something, but more or less, right? So now this fact that your classical computer and Turing machine does all the computation, this is called what hypothesis? This is called Church-Turing hypothesis. Okay, so Church-Turing hypothesis says whatever computation you can do can be done by a Turing machine, right? And now when we say that quantum computer can do better, then the first hope would be quantum computer can do computations which classical computer cannot do. At least it's true, but even if it is doing something new, we might be excited, right? We anyway have a classical computer. If quantum computer does something else, we would be happy, right? So then the first hope would be that quantum computers break what we call this weak church Turing hypothesis. It can compute, QC can compute what CC can't. What is CC? Classical computer, right? Anyone has the answer for this? Can this happen? The answer for this, okay, the reason being, at least in terms of computational tasks, whatever quantum computer can do, it can be simulated by a classical computer, though in a long time. Okay, so it's not as though what classical computer can never do, quantum computer can do in a finite amount of time. That's not going to happen. It is known that classical computers can be simulated by quantum computer, quantum computers can be simulated by classical computer. The issue is when you simulate classical computer with quantum computer, it is efficient in the sense that if for some computation classical computer is taking t time, quantum computer will take 2t or 4t time, not much more than that. Unfortunately, the reverse simulation, this is not. That means if your quantum computer is taking t time, classical computer can take huge amount of time. We don't even have a bound of t cube or to the power 4 or to the power 100. Okay, and this is where the promise of quantum computer lies. Better means more resource efficient. Okay, that could be mostly in terms of time, as someone already pointed out. Yes.
We have the same 3D machine model for quantum computers, or we have different model?
We have a different model for quantum. So this is called quantum Turing machine. Fortunately or unfortunately, we don't deal with it much. In classical case has circuit model also, right? We deal with quantum circuits. While we design algorithms, quantum circuits are much better way to design it rather than quantum Turing machine. So there is a, sorry, yeah, whatever you can do on a quantum Turing machine, you can do on a classical Turing machine. But the time might extend, the steps might extend. There is a quantum, there was some Deutsch in I think 86 or something, made a Turing machine, and then people said, oh, this is true, everything is fine, but you don't want to use it, you want to use circuits. Okay, and that's why we will study circuits in detail. Great. Okay, so where are we? We know what is quantum computer, we know why it can be useful, because quantum computer can be more resource efficient than classical computer. By the way, there is a name for this corresponding hypothesis also. This is called strong church theory hypothesis. So strong church Turing hypothesis says whatever you can compute on the Turing machine efficiently. We hope quantum computers can break it. Quantum computers can do calculations much more efficiently than a classical computer. Okay, and again we will see multiple evidences of this. No, as I said, quantum computer can always simulate a classical computer factor loss. So anything which you can do on a classical computer, you can do it on a quantum computer with, let's say, twice or 4 times the time. That is no. The other way is the separation we want. Questions? Yes.
Please explain the strong church hypothesis.
What did Church Turing hypothesis said? Church Turing hypothesis said whatever computation you can do, it can be done by a Turing machine. What strong Church Turing hypothesis is, if you can do a computation in a certain time, Turing machine can do the computation as well as it can do it in that time times some factor or some polynomial of it. So it can do it efficiently. So there will be no loss in the time also. When I say no loss in time, it doesn't mean t to t. It could be t to 2t, it could be t to t square or something. So strong Church hypothesis says, let's say you have a device which might not be a classical computer, it might be any device. It does computation in t time, Turing machine can simulate it in some related t time only. And that's where quantum computers seem to come. They say that these are special pieces of hardware which can do things much faster than a Turing machine or a classical computer. Okay, so till now I have been telling you things and you are believing me because I am a nice guy. Let me say more, let me at least outline a brief history of quantum computing. Okay, right? Brief history of time. How many people have read it? Good, good. Okay, there is not much generation gap between us, me and you. Nice to know. Okay, so we will talk about brief history of QC. Again, we are going to go into technical details throughout the course, but we will give you an
जहाँ तक मैंने पढ़ा है, Feynman used to believe that we can easily simulate quantum chemistry.
exactly. So Feynman's motivation was simulating quantum systems. What do I mean by simulating quantum systems? Suppose I have two electrons in certain quantum states, they are colliding together, they give you some other state, you want to know, you apply some electric field, magnetic field, what will happen after 10 seconds, right? Unfortunately, the state space for these quantum states are too big. The classical computer takes a lot of time to simulate these things, right? And if you actually want to know what system, what is your state after applying this electric field, magnetic field, the best way is actually to create these electrons in the certain state, collide them together, measure what is happening in the end, right? The closest to that is actually a quantum system which follows similar laws. That's why Feynman kind of thought that, oh, my problem is he was a physicist. He didn't care about factoring. He did not care about searching, sorting. He cared about, can I simulate quantum systems faster? And clearly it seems quantum computers are going to be able to simulate quantum systems much better. And till now, this is still our best application. Okay, simulating quantum chemistry, quantum mechanical systems. Okay, even the small quantum computers are able to do it in a certain way. So simulating quantum systems was okay, but then if that was the only thing, we won't get interested in this, right, as a computer scientist. So what happened in 1980s was people came up with quantum Turing machine, the formal definition of what a quantum computer is, what it can accomplish and things like that, and more importantly, to give a bait to us, it means this decade showed some examples. Obviously examples mean computation. Which are faster on QC. The problem with these computations were they were actually very artificial. They were not natural computational problems. They kind of created the problems so that they can show quantum computer advantage. Okay, so at least what they were able to show is that in certain models, quantum computer is more resource efficient than a classical computer, right? And that made things interesting. We don't know whether my problem is going to be solved faster on a quantum computer or not, but at least there are some problems which are faster on a quantum computer. Computational problems which are faster on a quantum computer. And these will be the first ones we will study. When I say first one, means around before mid-semester. Once we learn the entire quantum computer model, 1970s, we'll come to 1980s, and we will understand simple natural problems, and I will try my best so that you can think of this algorithm by yourself. Okay, that's why it is going to take so much time. And then the third step will come in which years? And here we actually came up with natural computational problems. This was, I think, the breakthrough year. This is where computer scientists said, oh my God, we have to look at quantum computers. There is no way we can ignore this thing. Because in this decade, we came up with natural computational problems which had quantum advantage. And do people know which algorithms I am talking about? Yes. So these problems are something which you would study in your first or second course of computer science, whether it is quantum computer or classical computer, doesn't matter, right? So these are natural problems which any computer scientist would study. And now someone is telling me, oh, in my problem set, there are problems where quantum computer does much better. Okay. Now everyone in the computer science world was listening. The progress in 2000s was slow, but they were able to extend, or I should say generalize these algos to larger domains. They said that the essential ideas used here can be extended to multiple problem sets. And even till now, most of the algorithms are actually coming from Grover's algorithm or Shor's algorithm. Even if you are excited about quantum machine learning, you might have seen many algorithms in quantum machine learning. Most of them essentially use these as the building blocks. So these are very important to understand. And then, and there was another algorithm which is used a lot in quantum machine learning. So you might hear it. This is called the HHL algorithm, which solves certain kind of linear equations fast. Okay, and this also uses Grover, but then this is directly also used in machine learning applications. So I just wanted to mention it. And after 2010s, there has been various ways in which quantum advantage has been seen. It has seen a lot of development in quantum hardware, and that's why you are hearing about it a lot of in the news, because now people are more and more ready to believe that there can be hardware on which you can execute these algorithms. right? And in this course, I will take you up to here. Somewhere in 2000s, I probably won't be able to cover HHL. Some of the things will be after 2000s. But most of this, if we have a small number of people in the course, we will do projects and you can cover some of the nice applications here. Okay, but I will make sure that you have enough fundamentals to read up on these kind of things. And also, the approach to learning these things would be slightly different. Most of the time, I would try so that you can come up with these algorithms. These come naturally to you so that you can develop more algorithms. Instead of telling you what they are, we will discover them. That's going to be the plan. Yes.
You mentioned that you might be working on some projects.
Yes.
Are these theoretical ones or practical?
If that happens, they will mostly be theoretical ones. Theoretical ones, yes.
I just wanted to ask, do we have any sort of hardware where we can do any practical versions?
Okay, so there are two kind of quantum hardwares. One is quantum simulator, one and actually the quantum computers itself. And now these companies say that you can take time on their quantum simulator or on their quantum computer. I have never been able to run things on their quantum computer. And then when you run it on quantum simulator, it's basically a classical simulator, right? So I'm not very excited about it. Though I will give you assignments, you will become familiar with this Qiskit system, how to give these things, but I don't think I'm going to focus on it a lot. So the projects will be mostly theoretical because I don't think we have access to Google's quantum computer or Amazon or IBM's standard quantum computer. But yeah, again, projects I'm generally very flexible. If you bring something exciting to me, I would be happy to help. I guess I'm almost with the technical part. So what we will do in the course, we will start with postulates. We have to learn a bit of quantum mechanics. I wouldn't even say bit of quantum mechanics, just few postulates. Basically, we will learn linear algebra needed to tell what is going to be our input, what are going to be our gates, what is going to be our outputs of a quantum computer. But that requires bit of math. I will go over some of them, but I will assume that you know almost all the basics already. Okay, once we know this, then we will understand circuits. Okay, classical circuits I will briefly talk about, but then we will take example of lot of quantum circuits. Those are going to be our quantum algorithms, and then we will see these 1980s algorithms. So this is kind of the part before mid-sem, and in between you will see a lot of different applications. Okay, small applications of the quantum circuit model. And then the big part will be Shor type of algorithms, Grover type of algorithm, and the exciting new thing which I'm going to cover this time, which is different and not covered in most of the quantum computing courses, is this talk about quantum advantage. What kind of problems can actually give quantum advantage, right? To start with, Grover type of algorithm, can you do better? Or is that the best you can do? So we will actually show that for search problem, Grover is the best. Now you can ask, if now I increase the size of problems, can I do better? What you will see is that you can do slightly better, but not exponentially better. And we will prove these results. So then we will actually end up with a class of problems for which we can potentially have exponential advantage. Okay, so this will require, obviously, algorithms we have already learned, but this will require proving lower bounds, because we have to say that quantum computers can solve this problem fast, but we also have to show classical computer cannot solve it fast, right? And those lower bounding techniques we will also learn. This is the plan for this course. I think another thing which is important is quantum hardware. People have obviously these questions that can we build a quantum computer? So what is your opinion? How many people think that we can build a quantum computer like you have a classical computer with, umpteen amount of qubits doing whatever calculations we want? Yes.
I do believe that.
Oh, you do believe. Okay. What is your reason for your believing?
Out of the technical advantage, because say a decade ago we did not able to comprehend like how it will quantum.
Very good. Yeah. So the progress in the quantum hardwares was pretty slow, right? So the concept started from 1970s or 80s. People tried to build it, and even in 2010s, we had quantum computers which had like 3 qubits or 5 qubits. But then recently, the progress has been very fast, and we can have even 1000 qubits, though this is not a full-fledged 1000 qubits computer in the sense that we can only apply gates on certain restrictions of these. Okay, actually, let me say that the two problems in building, and again, my knowledge in this is very, very limited. This is from going to conferences and hearing physicists and electrical engineers talk about it. So take it with a pinch of salt. These are the two biggest problems in building a quantum system, right? And you remember what was a quantum computer? You wanted to encode your laws of quantum mechanics into a quantum device, right? Sorry, encode your computation in a quantum mechanical laws, but that means you want to control the quantum devices. For example, remember the roe insect? If you want to build roe insect, what do you need? You need enough supply of insects with ring, without ring. You will be able to, should be able to apply injections to them, mate them. You should be able to see whether someone has ring or not. Same thing with quantum computer. Can you create systems which have required quantum state? Can you apply your quantum operations to it? Can you get output from them? But for that, you have to do it on very, very small systems. Unfortunately, two problems arise: stability. These states, there is someone talked about coherence, right? So these systems, they change their state even before you can finish your computation, right? So you might have 10 qubits, you are applying your operations, but before you apply the operations, things have not remained in your control. They have changed their state. And other thing is scalability. Generally in classical computer, you have one chip. You want more power, you have 2 chips, you have 3 chips. That doesn't work in quantum computer. You have to go from 50 qubits to 100 qubits is a big, big jump. It's not simply putting 250 qubits together because of something we call entanglement. Okay, so that's why these are the issues. And when you hear 1000 qubits computer, 100 qubits computer, it's not that 1000 qubits computer is better than 100 qubits computer. Some of them will have all possible operations allowed, some of them will have only local operations allowed, and people are trying to take care of these two problems in many different ways. And that's why most of these developments are exciting, because in some dimension they are making a progress, and there has been a lot of progress in both these dimensions. And that's why hopefully we will have a quantum computer, like a full-fledged quantum computer, probably not on your desk, but in every department in our lifetime, in my lifetime. Your lifetime you will have, in my lifetime. Okay, so this is what I know about hardware. So I will stop here.